Chapter 2.2, Basic Differentiation Rules and Rates of Change, Day 4. How do you find velocity, also known as the speed of an object? Well, speed, or velocity more appropriately, because it has direction as well as speed. Velocity is the change in position over the change in time. All right. Well, if P of t is a position function, how would you know the velocity? Well, first, we would have to have two times. We could say time ranges from A to B, or you want to look at it as a calculus way we've done before, time and then a little bit more time, t plus change in time. Looking at this approach, we got velocity equals the position at time B minus the position at time A over the times B minus A subtracted themselves. If we look at this statement of time, we could say the position at time plus change in time minus the position at time over time plus change in time minus time. Or, just to kind of simplify it, the top will stay the same and the bottom, the time and negative time will cancel each other out. P of t plus delta t minus P of t all over delta t. Now these two formulas should look pretty familiar to you. All right, they're the average velocity formulas. Let's look at a problem. Find the average velocity for P of x on the interval from 0 to 2. Graph the answer. Well, first, let's find the average velocity. All right. Using our formula, we got P of 2 minus P of 0 all over 2 minus 0. Well, P of 2 ends up being 8 minus 8 plus 2, so that's 2 minus P of 0. Those will cancel because they're 0. 2 minus 2 over 2 minus 0, which is 0. So the average velocity of the function from 0 to 2 is 0, meaning it doesn't change position. Let's take a look at this graphically. So here is our graph of the position function. And if we look at our position function, position at time 0, position at time 2, and notice how the average velocity on the graph ends up being the secant line. And we found in the last couple lessons that the secant line estimated the slope between 2 points. Well, using this, can we find a better estimate of velocity, aka instantaneous velocity at a point? What do we do for the secant line to make it a better estimate? Well, we took the point and we moved it closer and closer and closer until the change in t approached 0. And then we had a tangent line. Well, if we do the same thing for our average velocity, let our change in time approach 0, what we got is instantaneous velocity. So to find the velocity of a position function, we're going to take the limit as delta t approaches 0 of P of t plus delta t minus P of t over delta t. What is this the same thing as? Well, this is the same thing as the derivative of our position function. The derivative of position is velocity. Or, in big bold letters, v of t equals p prime of t. Let's do a few problems. A particle moves on the number line shown. This is its position function. All right? When is the position moving to the left? Well, moving to the left, left is in the negative direction. So when we're moving left, we'll have negative velocity. And since velocity is the derivative of position, and derivative is slope of the tangent line, we want to see where our slope is going down. That'll show us where the position or the particle is moving to the left. Well, we're going down on this interval here and this interval here. So we're moving left on 2 to 3 in union with 5 to 6. Where's the particle moving to the right? Well, for the right, we want positive velocity, aka a positive slope. We have a positive slope right here from 0 to 1. And where is the particle standing still? Well, the particle is standing still when we have a slope of 0. Particle is standing still on the interval from 1 to 2 in union with 3 to 5. A particle moves along the line so that its position at any time greater than or equal to 0 is given by the function s, where s is in meters and t is in seconds. Find the displacement during the first 5 seconds. That's what is the position, change in position during the first 5 seconds. So the first thing we're going to want to do, to find displacement, we want to have s of 5, and we want to have s of 0. That'll find our displacement. If we subtract those two values, that's our displacement. S of 5, we got 25 minus 15 is 10 plus 2 is 12. S of 0, 0 should always be easy to plug in, is 2. So our displacement, S of 5 minus S of 0, is 10. For average velocity, we're going to want displacement or change in position over change in time. We've already calculated our change in position. Our change in time is 5 minus 0, which is 5. So our displacement is 2, and we should always include units. Displacement is meters. Average velocity is meters per second. For letter C, find the instantaneous velocity when t equals 4. Well, instantaneous velocity, we need the derivative. So we'll need to find s prime, which will be our velocity. And applying the power rule, we get 2t minus 3 is our velocity function. So the instantaneous velocity when t equals 4 is 5 meters per second. One more set of examples. A particle moves along the line so that its position at any time greater than 0 is given by the function s, where s is in meters and t is in seconds. Units are important. Find the instantaneous velocity at any time. Instantaneous velocity, you should think, oh, derivative. So, oh, let's find our derivative. V of t, or s prime, however you choose to label it, should be 3t squared minus 12t plus 8, and then the derivative of 2 is 0, so we don't need to write it. I skipped question B, obviously. C, when is the particle at rest? Well, when you're at rest, what's happening? Personally, when I'm resting, I like to be sitting around doing nothing, not moving. So the same thing with a particle. A particle is not moving when it's at rest. In other words, the velocity equals 0. So we're going to do, when is a particle at rest, set the velocity equal to 0, and solve for t. Then there's a couple ways to do this. I think the most effective way is to go ahead and use your quadratic formula. So we got 12 plus or minus 12 squared minus 4 times 3 times 8 all over 6. Let's punch that out here. Do the discriminant first. Discriminant is 48. So we'll have 12 plus the square root of 48 over 6 for 3.155 seconds. Let's go back up and grab that same equation and change our addition to subtraction. And we got 0.845 seconds. So the two times that this particle is at rest, 3.155 seconds and 0.845 seconds. So in review, velocity, average velocity more specifically, that is the slope of the secant line. That'll find your average velocity 2 points. P of B minus P of A over B minus A. Or, if you want to go with time plus delta time, P of T plus delta T minus P of T all over delta T. And then instantaneous velocity, well, that is your derivative. And to find the derivative, you just take the limit. In the first one, B approaches A. And in the second one, delta T approaches 0. So to find velocity, we're going to find the derivative. Instantaneous velocity is the derivative. Average velocity is the secant line.